Okay, we have a few preliminaries, so let's go ahead and get started. So I welcome those of you who are joining us today. My name, for those of you who don't know, I'm Walter Sterling. I'm the Dean of St. John's College in Santa Fe, and I'm happy to welcome you to this installment, the Dean's Lecture and Concert Series. And I'll say, as I have been, that it's one of the consolations of this year that we're able to come together this way and continue to learn from one another and have conversation and to bring together members of our community far and wide from both campuses, students, faculty, staff, and alumni. And so welcome to all of you who are joining us. And maybe it's especially consoling, as many of us are more locked down again, that we can find ways to reflect and connect in this fashion. So as many of you know, we have a tradition of not introducing our own. Were we in the Great Hall in the Peterson Student Center, Mr. Fisher would just walk up to the front of the room and begin speaking. But in this environment, I at least like to say a couple of words. So I want to thank my friend and colleague, Howard Fisher, for the second time that he's offered to lecture. He was one of our first to venture into this format in the spring after the disruption with a lovely talk on Maxwell and Faraday, and we welcome him back today. Howard Fisher has been a tutor at St. John's College since, I believe, 1965, teaching as an active member of the faculty until 2007, many years in Annapolis and then many years in Santa Fe. And he's now tutor emeritus, and he also serves as an editor, I believe, at the Green Lion Press. And I'd like to mention that he's edited and written commentary for two very important texts for us, one by Faraday and one by Maxwell, absolutely central to our work in the St. John's College Laboratory Program. And both of those are published by Green Lion Press. As I said before, Mr. Fisher is one of our faculty who's been most generous and most attentive to the development of our lab program over the years and decades. So I'm grateful that he's willing to share more of his reflections on that subject matter today. Now, I'm going to say a couple things about format, and then I'm going to let Mr. Fisher just say a word or two. We are going to have a recorded live event today. So Mr. Fisher has pre-recorded the lecture, and in a couple of moments, I will share a link to YouTube where you can view the lecture, which will be about 45 minutes. And then we will return to this very webinar for a live question period. And you could key that to 5:30, which should give you a few minutes, give us all a few minutes of break in between. And the lecture was pre-recorded and posted that way to avoid challenges with streaming video, and also because of the material Mr. Fisher wanted to present could be done more effectively in a pre-recorded way. I also want to mention we will have a couple more lectures this fall. We have one currently scheduled for this Friday, but I think some scheduling and logistical challenges mean that that is going to get rescheduled for after Thanksgiving. A notice will go out on that, but that is Bree Wooten lecturing on Aristotle's De Anima, and I believe it's going to be rescheduled from this Friday to a date after December 1st. We also have Diana Schaub lecturing on Lincoln and Douglas, and that is going to be on Friday, December 4th. I think those are the two events we currently have scheduled for the remainder of this semester. With that, Mr. Fisher, is there anything you'd like to say to welcome our guests before we send them off to watch your lecture?
Only thank you everyone for being here. And as Walter mentioned, there are a number of video clips in the lecture. They don't play very well over Zoom, so this asking you to go temporarily to a YouTube site and then come back is our way of meeting that challenge. Welcome everyone, and thank you for joining me this afternoon to think about the magnificent pendulums. My talk will have 5 parts. This is part 1, that same again feeling. There is something captivating about repetitive actions. What is it? Is it perhaps the regularity of such events? Think of the repeated drip, drip, drip of a leaky faucet, how it captures the consciousness and may even drive a person to distraction. But mere regularity, I think, is not the reason. The second hand of this clock advances regularly every second. A prolonged encounter with it is rather boring than captivating. But the pendulum of a clock is a different matter. Its motion does tend to ensnare our awareness. The forth and back motion of the pendulum draws us in, but the endless forward progress of a clock's second hand puts us to sleep. A motion forward and back returns to its beginning, and thus defines a completed act. Endless progress, in contrast, never reaches completion. It is forever only getting started. Completeness, I think, is what draws our notice. That may be the reason why a repeated sound commands more attention than a repeated motion. The sight of our clock's second hand intimated no conclusion, no wholeness. But its sound alone, like that of the dripping faucet, begins to lay hold of our consciousness. Without the sight of a clock face to announce that there really is no end to circular motion, each tick of the clock can seem to be a whole in itself, and that, apparently, is all our consciousness needs to capitulate. For all its appeal, though, the pendulum's motion is not easy to apprehend. Indeed, the wholeness of each swing seems, by comparison, to overwhelm our ability to grasp the successive moments of each motion. Let's see how much we can grasp with the unaided senses. First, it certainly appears that every swing of this improvised pendulum takes the same time as every other swing, so that the body's repetitive motion marks off equal intervals of time. And to the extent that each full swing returns the suspended body to the same position as that from which it began, it would be astonishing if every swing were not identical to every other in all respects, since from the same conditions we expect the same results. But of course a swinging body does not, or not quite, manage to return to its starting position. Sometimes this loss is detectable in the very first swing, but even when it is not, we know that every swing must suffer some loss of motion, since the body eventually loses enough motion to make the decrease evident. So it is not clear that our sense of same again is entirely reliable. I think we can also probably grasp that the pendulum momentarily stops at the extremity of each swing. Even so, however, it's not clear that we understand this by sight alone. For what we clearly see is that it reverses direction at the extremities, and Aristotle, in his discussion of continuity, shows how reversal necessitates momentary cessation. So perhaps our sight stimulates an intellectual apprehension so swift, and to which we are so accustomed, that we overlook it and attribute our judgment to sight simply. Another distinctive phase of the pendulum's motion is its central position, where we may persuade ourselves the pendulum achieves its greatest motion. Again, though, we may doubt whether we actually see this. For the symmetry of the pendulum's path would seem to necessitate such an inference, as would likewise our realization that the central position of a pendulum is also its lowest position, and therefore the place of maximum speed, as Galileo showed for falling bodies in general. Again, I am not questioning the truth of these conclusions, but only whether we apprehend them by sight alone. Even with reason's aid, however, when it comes to the intermediate positions of the pendulum, what can we say of them? To be sure, we know how to measure. Suppose, then, we undertake an exhaustive series of measurements, and so gain accurate knowledge of the pendulum's position at precise individual times. Without some grasp of the overall character of pendular motion, these are mere isolated factlets. They present, as Socrates would say, a swarm of bees rather than the nature of bee. What we really want is something like the nature of the pendulum. That is, if it had a nature, rather than being, as it is, not natural, but artificial. But the very fact that an artificial apparatus invites us to look at it as though it were natural is already interesting. You may have noticed something else as the pendulum's motion decayed. The time occupied by each of the small swings was not very different, if indeed at all different, from the time marked out by each of the original large swings. Let's investigate this more exactly. Here are 5 swings from the first few minutes of the previous video. When we time them, they occupy 6.60 seconds for an average of 1.32 seconds per swing. And here are 5 swings from much later in the same video, when the amplitude of each swing has noticeably decayed. Now the time for the same number of swings is 6.53 seconds, or 1.30 seconds per swing. Not quite equal, but certainly very close. We will ask later on whether the difference is significant. For now, though, it appears that every undulation of the pendulum occupies pretty much the same interval of time, without regard to the size of the swing. This is the property called isochrony. Galileo is said to have noticed this phenomenon when he was a student in Pisa. The Pisa Cathedral was illuminated by large suspended oil lamps, which would occasionally swing back and forth. Sometimes the movement was small, other times much greater, but small or large, the time occupied by each swing appeared to be the same. The lamp shown here, part of an Italian promotional video, is called Galileo's lamp by the tour guides. We can be confident that the real Galileo's lamp was not electrified. Nor does this lamp readily sway to and fro. In fact, it isn't Galileo's lamp at all, having been installed about 10 years after he supposedly made his observations. But it is nonetheless lovely to look at, and evidently somebody at the Pisa tourist office thought it was worth 1 minute and 12 seconds of video, so perhaps it is to us as well. Part 2. The Pendulum Clock. A device that divides up time into equal parts is a clock, and you can see how valuable the property of isochrony would be in a pendulum clock, since its accuracy would then not depend on every swing describing the same size arc. The problem for the clockmaker then would become simply to keep the pendulum swinging. But how to do that without interfering with the regularity of its swings? Well, we know how, at least in principle, for it is what every parent has done when pushing a child's swing. If we time the pushes just right, the swing maintains its motion, either soothing or thrilling. But if we apply any of them too early or too late, the motion becomes erratic, and the child soon announces its righteous displeasure. In a classic pendulum clock, the slow descent of a weight, or the protracted unwinding of a spring, is converted into a series of well-timed pushes by a triggering mechanism called the escapement, of which there are numerous designs. The very first pendulum clock, Huygens's clock of 1656, employed what is now called a verge escapement. In Huygens's drawing, the pendulum, marked V at the right, is pivoted at the top and swings in and out of the plane of the screen. The heart of the mechanism is the crown wheel, whose circle of vertical teeth gives it that name. A train of gears connects the crown wheel to a descending weight, and were the wheel not periodically engaged by the angled pawls, marked L, it would spin without interruption. But as the drawing shows, the pawls are mounted on a horizontal axle that is coupled to the pendulum. As the pendulum oscillates, this axle rotates back and forth, and with each half-swing of the pendulum, the pawls bear alternately against the vertical faces of successive teeth, so that each receives a gentle nudge as the tooth passes by. The axle transmits this nudge to the pendulum at the same point in each swing, thereby replenishing the motion which the pendulum would otherwise lose during each swing. Let's watch the mechanism at work. This clock escapement was built nearly 2 centuries after Huygens. We are looking down upon the crown wheel. Notice how the pawls are brought alternately to bear against opposite teeth. Each quarter turn of the axle corresponds to a half swing of the pendulum. By the way, the verge escapement takes its name from this axle, called the verge, from Latin virga, a rod or stick. Many smaller clocks and watches employ some version of the anchor escapement, so called because of the anchor-like shape of the cog that carries its pawls. Here is a variation of the anchor design, in which filed edges of a bent rod constitute the pawls. I hope you can see how the angled ends alternately stop and are then pushed out of the way by successive teeth, each time receiving a nudge that is transmitted to the pendulum. That escapement was widely employed in mantle clocks like this one. The clock in this photo belonged to my maternal grandfather, Hyman Schengold, who was himself a watchmaker. I should explain that in the 1920s, a watchmaker was really more of a watch repairman. Watches, and most clocks, were mass-produced in factories like this one in Waltham, Massachusetts. But they required constant adjustment and cleaning, and it was the watchmaker who performed these services, as well as more elaborate ones, such as replacing springs and gears. The escapement of my grandfather's clock is not visible without disassembly, but the pendulum is. Here it is in operation. The pendulum is mounted on a ribbon of spring brass, which eliminates the friction and wear of a pivot and bearing, while being weak enough to exert negligible effect on the pendulum's period. The period of this model is 0.723 seconds. Part 3. Pendular motion. We know how to keep a pendulum moving, but what precisely is the motion we are preserving? what kind of motion does a pendulum actually perform? As I noted earlier, this is not the kind of question we can answer by measuring a series of positions occupied at successive times. It is a question about what essentially characterizes pendular motion. And to that extent, it is like asking about any of the characteristic behaviors of a cat. Not a question to be answered by measurement, though measurements can contribute to finding an answer. Compared to pendular motion, the two motions studied by Galileo in the two new sciences are simple indeed. Uniform motion, which traverses equal spaces in equal times, expresses its essential character in the single defining property of constant velocity. Once we know that property, particular circumstances like the direction or the duration of the movement are just ancillary details. The motion of bodies in free fall, similarly, has but a single defining property, constant acceleration, that is, rate of change of velocity with time. When the three friends depicted in Galileo's dialogue seek definitions for those motions, it is precisely these essential characters they are trying to identify. Uniform motion is maintained, at least for limited periods of time, by bodies that glide on a horizontal plane. Uniformly accelerated motion, Galileo shows, is exhibited not only by bodies in free fall, but by those that glide on an inclined plane. But pendular motion traverses a circular arc. Its acceleration not only fails to be constant, it does not even change at a rate that is constant. If we hoped to discover in pendular motion a single definitive rate of change, we shall be disappointed. As we shall see later, no characteristic of the pendulum exhibits a constant rate of change. When Plato's wise legislator undertakes to craft just laws, he looks, at least to the extent possible, to the form of justice. Just laws will, again to the extent possible, mirror the form. And to the extent that we can see the form reflected in the laws, we will understand both what the laws aim for and to what extent they fall short. But if we have no inkling of justice itself, we will have nothing upon which to base our judgments except the contentions of itinerant ideologues, or the passing fashions of our own circle of society, which is likely to be narrower than we believe it to be. That, it appears, is our situation with regard to the pendulum. We do not see a form to which its distinctive motion aspires. But what if we were to discover a kind of motion which does seem to be reflected in the pendulum's motion, and one which, moreover, appears to possess a degree of unity and intelligibility that the pendulum's own motion does not itself display? I believe we can all experience such an elevation of vision with the aid of a simple mechanism. Here is a pendulum consisting of a wooden ball mounted on a slender rod. Its effective length is about 31 1/2 inches, which, at the elevation and latitude of Santa Fe, causes it to swing out and back every 1.8 seconds, or 33 1/3 times per minute. Its motion is being continually replenished by a clock drive mechanism, except that in our technological era, the mechanism is electronic. The machinery that Hyman Schengold would have had to repair with individual brass gears and precision bearings is now a plastic frame and circuit board that, like so much else, is far cheaper to replace than to repair. If you are old enough to remember long-playing records, which my generation called LPs, the figure 33 1/3 will be familiar to you, for 33 1/3 revolutions per minute was the speed at which LP turntables revolved. I'm going to place such a turntable directly beneath the pendulum, with a small post mounted on the turntable directly beneath the release point of the pendulum, and watch what happens when we start both motions together. One full swing of the pendulum coincides with one revolution of the turntable. And when we crouch down to view it from the side, the pendulum follows at every moment the motion of the post, or pretty close. Something very much like this, I imagine, was experienced by Plato's cave dwellers when they turned their heads away from shadows and saw for the first time the objects that cast them. Pendular motion, we suddenly understand, is a nearly one-dimensional reflection of regular circular motion, which is two-dimensional. Can we be like Plato's wise legislator? Can we come to understand the essential character of pendular motion by looking at the form or paradigm of that motion? Let us try. Part 4. The Para-digm Circle. Let the circle in this slide depict the rotating turntable, with O representing the spindle and M the post. When we viewed the apparatus from the edge, we saw only the left and right motion of M. Its toward and away dimension was lost to us. What we saw in the side view can be represented by a fixed point O', the image of the spindle, and M', the image of the post, moving left and right along the straight line between the extremities C and D, with central position O'. The length CD is the amplitude of the swing, and of course it is equal to the diameter of the circle. But at every moment, the swinging pendulum coincided vertically with M'. The line O'M', which is the distance of the pendulum from its center, is therefore only an image of the radius of the circle, and the motion of the pendulum is but an image of regular motion about the circle. Taking regular circular motion, therefore, as the paradigm of pendular motion, generations of Johnnies have called this circle the Para-digm Circle. Since one full swing of the pendulum corresponds to one rotation of the circle, the period of the pendulum swing, forward and back, is the same as the time of rotation. Let us call it tau. We have now at least part of what we were looking for, a unifying image with which to characterize pendular motion. And in particular, we can interpret the ever-varying position of the pendulum by referring it to the strictly regular rotation of radius OM. But we can do more. At M, draw MQ tangent to the circle and equal to the velocity of point M, or, what is the same, the rate of change of radius OM, in direction only, since OM is constant in length. Then draw ON equal and parallel to MQ. Thus it is clear that ON likewise represents the velocity of point M. Then, just as O'M', the image of OM, expressed the pendulum's distance from the center at any moment. So too O'N', the image of ON, expresses the pendulum's velocity at the same moment. So we can know instantly that if the pendulum is at M', its velocity is O'N'. In particular, it is obvious that the pendulum has maximum velocity at the center and zero velocity at the extremities. Of course, we had already nourished intimations of this fact, but now we are gaining it through clear sight. We are seeing truth, or about as near to that as we are likely to get unless we may someday join the banquet of Plato's blessed gods, and with them rise up to the vault of heaven to be nourished by gazing upon truth. Of course, I'm quoting from Phaedrus 247. There is no need to stop at this level. At N, draw NR tangent to the circle and equal to the velocity of N, and proceed as before to draw OP equal and parallel to NR, so that OP also is the velocity of N, that is, the rate of change of ON, while ON in turn is the velocity of M. Then OP is the rate of change of the velocity of M. It is the acceleration of M. Finally, just as O'M', the image of OM, represented the pendulum's distance from the center, we recognize that O'P', the image of OP, represents the pendulum's acceleration. Since M and P must always lie on opposite sides of center O, we instantly grasp, by sight, that the pendulum's acceleration is always in the direction opposite to the direction of the pendulum's displacement from the center. Moreover, it is always proportional to that displacement, since the circles revolve without changing their radii. Wherever the pendulum is at any moment, it is accelerating towards the center, with an acceleration proportional to its distance from the center. This proportionality has every appearance of being an essential principle, which the Para-digm Circle makes manifest when carried to its threefold development. For that reason, I want to make a distinction now, whose importance will emerge later. The line O'M' is not merely a distance. It is the path that must be traversed if the pendulum is to reach the center. At the present stage of our reasoning, we are supposing that path to be a straight line. But if we wish to apply the Para-digm Circle to a body that moves along a curve, the distance O'M' would have to represent curvilinear or arc distance. That consideration, however, may serve to plant in us some doubt about the ordinary pendulum, since its path is, in fact, a curve. Once we have appreciated the proportionality between acceleration and distance to be traversed as an essential principle of pendular motion, we can state it in a quantifiable way. Since each member of the threefold Para-digm Circle completes one revolution in one period tau, the speed of point M on the outermost circle will be 2 pi times OM over tau. And since that speed was represented by ON, we have ON equals 2 pi times OM over tau. That is, ON over OM equals 2 pi over tau. In the same way, the speed of point n on the middle circle is 2 pi times ON over tau. And since that speed was represented by OP equals 2 pi times ON over tau. That is, OP over ON equals 2 pi over tau. Thus, the quotients OP over ON and ON over OM are equal to one another, and each is equal to 2 pi divided by the period. Combining x equali, we have OP over OM, that is, acceleration over distance, equals OP over ON times ON over OM, which equals the square of 2 pi over tau. Thus, the ratio of acceleration to prospective path distance is not only an essential principle of pendular motion. The size of that ratio actually determines the period. Nor is that all. If this is a feast for the intellect, like that of which Zeus and the blessed gods partake in the Phaedrus, there is here abundance of nourishment. Since the ratios OP to ON and ON to OM are equal, the triangle formed by joining MN and NP is a right triangle. And it is clear that we can continue the pattern to construct an unending rectilineal spiral, finding more and more circles within circles without limit. And these will represent an unlimited number of rates of change, of rates of change, of rates of change, on and on, without ever reaching an end. Now we understand why we found pendular motion so challenging to grasp. When we began, we knew of only one way to understand motion. That was Galileo's way of finding a constancy underlying the change, as when he identified first constant speed and then constant acceleration. But that method, when applied to the pendulum, turns out to be an infinite task. But the discovery of the Para-digm Circle, may I call it Plato's way, invites us instead to discern a unity instead of an infinite sequence. But where in all this is that marvelous property of isochrony, which Galileo observed in the swaying lamp, and we witnessed in our earlier pendulum video? There, you will recall, the pendulum swing took the same amount of time, regardless of its amplitude. The Para-digm Circle expresses isochrony by turning with the same speed regardless of its size. But does it necessarily turn with the same speed regardless of size? Well, we could point to the fact that the definitive ratio which determines the period, the ratio of acceleration to distance, makes no reference to the radius of the circle. And therefore, we might argue, the speed with which the circle turns should be independent of the pendulum's initial displacement. And that independence, we may contend, is what secures isochrony. This seems to me a disappointingly weak argument. The absence of any connection between the speed of rotation and the size of the circle shows only that isochrony is consistent with the paradigm. But I would have expected such a universal and apparently fundamental characteristic of the pendulum to be embedded in the paradigm. That it is not is to me just as astonishing as if we were to behold the Platonic form of cat, but fail to find anywhere in it the propensity to chase mice. Then is isochrony, after all, not an essential characteristic of pendular motion? Yet, if not, How does it come to be such a universal property among pendulums? Part 5, the last part. Natural acceleration. Long after the young Galileo's encounter with the swaying cathedral lamp, he made systematic studies of the pendulum. These, however, while meticulously confirming the fact of isochrony, allowing for the effects of air resistance, did not undertake to explain it. Nor perhaps should we expect him to do so, since his propositions in the third day deal with uniform acceleration, while the pendulum obviously undergoes varying acceleration, since it traces out a path having varying slope. Nevertheless, Proposition 6 of the third day, page 221, seems at least suggestive of pendulum isochrony, since it establishes isochrony of descent along chords of a circle. Galileo's drawing is shown on the left, and the proposition may be paraphrased this way. Let AC and AD be chords of the same circle. If bodies are released from rest at C and D, they will descend along chords CA and DA in equal times. This does not bode well for the pendulum, for if the pendulum bob is suspended from center O, it will descend along the circular arcs CA or DA, not along their chords. But if the descents along the chords are isochronous, it is hard to see how descents along their arcs could be isochronous too. And if you recall the pendulum timing test we made earlier, the period for the larger swing was in fact greater than that for the smaller swing by about 1.6%. Nevertheless, as arcs become smaller, the more nearly do they coincide with their chords. And so simple pendulums ought to become more nearly isochronous the smaller we make their arcs. This is an inference we can make directly from Galileo's Proposition 6, and it surprises me that Galileo did not. In fact, one of Galileo's proofs for Proposition 6, the one he describes as based on mechanics, reveals a proportionality between acceleration and distance reminiscent of the proportionality we found in the Para-digm Circle. For consider any chord, say chord DA. Join BD as in the diagram on the right, and drop DE perpendicular to diameter AB. Now Galileo had already established that the acceleration experienced by a body gliding on chord DA is to the acceleration of free fall as EA over DA. But the acceleration of free fall is constant. Therefore, the acceleration along DA is itself proportional to EA over DA. And by similar triangles, EA over DA equals DA over BA, while diameter BA is constant for a given circle. Therefore, the acceleration along chord DA is proportional to DA. That is, acceleration is proportional to distance, just as we found in the Para-digm Circle, except now for uniform rather than for varying accelerations. Apparently, it is not the Para-digm Circle itself, but the proportionality between acceleration and distance that underlies isochrony. We effectively built that proportionality into the Para-digm Circle when we supposed the circle to rotate at a fixed speed. But now we see that the same proportionality can obtain with the same isochronous results even when there is no periodic motion at all. The Para-digm Circle is indeed paradigmatic for pendular motion, even though the simple pendulum doesn't quite live up to it. But the roots of isochrony appear to lie elsewhere, in the realm that Galileo calls mechan-ical, that is, the motions of bodies insofar as they act upon or are acted upon by other bodies. Since it turns out that the simple pendulum does not actually execute pendular motion after all, perhaps we should abandon that name. The term that is now standard for the motion defined by the Para-digm Circle is simple harmonic motion, a title that is, to most present-day readers, simply opaque. In contrast, a body that executes simple harmonic motion has a name that is easy to understand. It is called a linear oscillator, after the proportional or linear relation between acceleration and distance. The simple pendulum then fails to instantiate the Para-digm Circle, but there is a pendulum that succeeds. Both Newton and Huygens were able to show that the path which genuinely secures isochrony of descent is not the circle, but the cycloid, a curve generated from the circle. In Huygens's construction, as circle SR rolls clockwise along the horizontal RV, the point R fixed on it traces out the curve RWV, a cycloid. Alternatively, if the dotted circle rolls clockwise along its horizontal, a point R fixed on it will describe cycloid RO. Huygens then proves that any tangent to the lower cycloid cuts the upper cycloid at right angles. That perpendicularity is the property which enables a suspended body to swing in a cycloidal curve, as we can see by inverting the picture. Huygens adapted this geometry to produce the first pendulum-controlled clock. Although mechanical clocks had existed since at least the 14th century, using a variety of regulating mechanisms, only Huygens's cycloidal pendulum incorporated a theory of isochrony. In Huygens's clock, the bob M is suspended from O by a flexible strip, but it is constrained between two cycloidal ears, OR and OV. As the pendulum bob swings to the right, the strip bears against one ear to become tangent at point T. The bob therefore traces out a path on the cycloid RMWV. From the inclination of the curve at each point M, we can show that the acceleration at that point is proportional to the arc WM. And since it is that very arc which the pendulum must traverse in order to reach the center, the cycloidal pendulum achieves that essential proportionality which the Para-digm Circle ordains, but which the simple pendulum can only approximate. Here is a drawing of Huygens's first clock, built in 1657. Its pendulum really is isochronous, even for wide swings such as the one depicted. And Huygens's pendulum clocks achieved far greater accuracy than did earlier clock mechanisms. But was that improvement due to the isochronous path of the pendulum, or to the pendulum itself, regardless of path? It turned out that, in actual cycloidal clocks, friction of the suspension strip against the cycloidal ears, together with other problems that came about with large swings and their resulting high pendulum speeds, outweighed the practical advantages of Huygens' theoretical improvement. It was less troublesome on the whole to restrict ordinary simple pendulums to small deflections. Is there a cautionary lesson here? Huygens' pendulum is a more perfect instantiation of the para-digm circle than the simple pendulum. But the simple pendulum functioned better. Suitably restricted, the simple pendulum turned out to be an alternative technological path, one equally directed towards the paradigm, but less obviously so, and which, perhaps for that reason, Huygens overlooked. That may serve to remind us that the work of ameliorating practical affairs is subtle. If our efforts are bent too doggedly upon mere imitation of the perfect, they may prove superficial, formulaic, and distracting. Granted that insight, or even a mere glimpse into the timeless, is what the soul craves, knowing when and how to blend that vision with the logic of the cave is an art in itself, one that well deserves to be both cultivated and cherished. Thanks, everyone.
Okay, let's see, Terry, I'm turning on your microphone. Are you there?
I am. Just wanted to remark that it was a remarkably good presentation, Howard.
Thank you. Terry and I are very old friends back to my high school days.
And mine.
And his, right.
Terry, did you have any further question or comment, or are you going to leave it there?
I'll leave it there, and if there's anything else that comes up, I'll gladly issue it.
Okay, very good. Well, I see we have another question from Mr. Stickney, who should be able to.
Can you hear me?
Yes.
Yes.
Well, many thanks, Howard. That was a wonderful talk, and I thought it revealed very well what a Platonist Galileo must have thought himself to be, and indeed was. That there are various kinds of clues throughout his writings. That even the choice of dialogue form, I think, suggests strongly that he must have loved Plato. And I remember as a student in the junior laboratory being especially delighted by a showing of a piece of clay revolving on a turntable whose shadow was what one could follow as perfectly matching the motion of the pendulum. And so that that moment of turning the three-dimensional, or a two-dimensional anyway, motion of the clay into one dimension by making it a shadow was for me a revelatory thing. It was great to see it again. I wanted to ask about another moment in your presentation in which you draw the tangent to the circle. Let us call it the circle of the turntable. Say, now let this tangent be the speed, and then you draw another circle inside that original circle, and a line from a radius of that circle that will be parallel to your original tangent. Yes?
Yes.
Yeah, it does show the things that one hopes it will show, and yet it seems for a moment, I sort of want to make the Hegelian complaint that one draws these lines and one gets the answer, but where did the lines really come from? How did one know at that point to draw a tangent and then observe the behavior of a line parallel to that tangent with an inner circle?
Yeah, but isn't that the kind of question we're constantly asking? Certainly in, synthetic mathematics like Euclid's. And I mean, wasn't that, forget Hegel, wasn't it Descartes' complaint? Right? Nobody tells us where these things come from. And it doesn't seem to me that Descartes' answer is an exhaustive one. It's merely a brilliant one. It seems to me that we get insights that such and such a thing will reveal more than we know. And it seems to me that happens a lot, but I don't know that anyone has ever given a really good account, or at least not a systematic account, of why that happens. In the case of this particular construction, it has a long history. I forget who invented the hodograph. I think it's a 19th century French device, but that's exactly what it is, to represent a directed quantity by what we now call a vector, and then put all of those vectors sharing the same origin. And the Para-digm Circle, as I developed it, is really a kind of simplified version of that. But where did that come from? I don't know the history of it.
Is there perhaps a kind of a suggestion that the circle be envisaged as an infinite number of infinitely small straight lines, one of which we are magnifying? I mean, are we already in our minds breaking down that velocity into a number of, that changing velocity into a number of microscopic uniform velocities, and as it were, letting there be a little tiny jump between each one, yeah.
Well, I suppose we must do that if we insist on making a connection between the instantaneous and the continuous. I'm not sure that the notion of the Para-digm Circle actually requires us to do that. Again, that's territory that I wish we could explore more. And I mean, you probably noticed I tried not to have a bit of calculus in this talk. Yeah. Calculus, of course, is the science that claims to bridge those. I'm not sure it's the only way to bridge them.
Mm-hmm. Mm-hmm. Yeah, well, I'm very grateful to you for presenting this to us. It was a wonderful reminder of, I think, one of the most wondrous parts of the whole St. John's curriculum, or maybe of the history of human thought. A marvelous thing.
I'm inclined to think the pendulum is, well, one of the best things the human race has ever come up with.
So right now we don't have another question queued up. It occurs to me to say that for some, this material might be a little challenging. Oh, Terry has decided to come back in, and then we've got something written. So let me take Terry's question, and then, okay, Terry.
Okay. Yeah. Can't we actually say that Euclid and the other geometers actually bridged that gap between the discrete and continuous by using a compass?
Well, do you think that a compass actually draws what Euclid calls a circle? It seems to me it just draws something close to a circle.
Well, yeah, but the paradigm that you're chasing with a compass is indeed a circle. Okay, so when you get down to the microscopic, and and look at the infinitesimals in it, you're of course seeing discrete points or little bits of graphite or whatever, but the concept is that of constraint on the direction that the pencil point of the compass is taking, and it's constrained by between the pencil point and the needle. That's what I'm trying to say.
Terry, I'm sorry, but you were breaking up a lot and I didn't hear a whole lot of that. But I gather that you think that Euclid doesn't really need calculus to live in the world both of the static and the moving. I would like to believe that. I can't quite convince myself of that yet.
Well, you've got to look at it this way. He dwelt in the domain of the living without calculus because he was, 1,800 years behind Newton.
Terry, you are breaking up some, so I think we'll take another question. I think might pick right up on that. We have a written question. Do you believe calculus obscures or reveals the beauty of the pendulum?
I would not credit or blame calculus with doing either. It seems to me that really depends on our own habits of understanding. There was a time when I thought calculus really revealed everything, but that was before I joined this community in which Euclid is such a bedrock of thinking. And that was also at a time before which I had studied very much Plato. And then I came to think just the opposite, that calculus was a really heroic attempt to do the impossible, and that was to represent what only geometry can really represent. And I think I've gone back and forth a number of times since then. So it's not showing me who the questioner is, but whoever you are, what has been your experience? Have you always felt the same way, well, whichever it be, about calculus?
Maybe while we're waiting to see if our questioner responds to that, we have Don Lemons wrote a question, but also raised his hand. I'm going to go ahead and unmute Don. Are you there?
Yeah, can you hear me okay?
Sure
Yes.
can. Hi, Don.
Hi. So I wrote a question. I answered it in my mind, but I'll go ahead and ask it. I was wondering, is it clear that the natural pendulum motion controls the action of the escapement? Or is there some cause and effect the other way? Like, could the escapement control the pendulum motion in some way?
Oh, definitely does. I mean, for one thing, the escapement provides the energy to the pendulum, which it would otherwise, be constantly losing. But I think the technical problem of a good escapement design, and I wish there had been time to go into this in the talk, is to find a way for the escapement to feed that energy to the pendulum without itself imposing motion on the pendulum. And most of the early escapements really were not very well, didn't perform very well because they could not separate those two things. I'm just forgetting the name of the escapement that, let's see if you can picture it. If I hold up this pencil, it revolved horizontally back and forth. It didn't involve gravity at all. Each swing of the device, whose name I've just forgotten, its timing was controlled by the time it took to accelerate the thing and then to decelerate it at the end of its swing. And, it did define a certain period of time, but that period depended on so many other factors that the weight, or the falling weight, if that's what it was, that kept driving this thing back and forth, also kept interfering with the period. So the pendulum that I showed in the talk, a variation on what they called the anchor design, is really one of the very best and most successful in delivering energy to the pendulum, but very minimally imposing its own influence on the pendulum's motion.
Yeah, thank you.
That.
Okay, we do have the hand raised by the beauty of calculus, or the obscuring or revealing beauty. Maybe you can introduce yourself, since I'm not sure that your pen name is your name.
Hi, my name is Michaela. It abbreviates it, but I asked that question because you made a lot of mention of sight and being able to see the motion of the pendulum and know it in your lecture.
Yes.
And I guess I was wondering, calculus or the mathematics and the way the junior lab manual kind of takes us through the motion of the pendulum is a lot of mathematical abstraction. So it kind of takes you away from the sight of it, and in a way reveals the phenomenon, but also kind of obscures what's actually going on with the motion. So I guess I was more curious about where you saw like sight, the math, how sight and math kind of interacted in the pendulum. Or
I think this is a question that one could raise about mathematics generally, of course, but I've seen two kinds of development of the calculus treatment of the pendulum. One is just straight from Newton's second law, and you can derive everything, right from it, and never use a single diagram. And again, for people who have become familiar with second-degree differential equations, that is just as transparent as any visual diagram. But for people who are not, I think, it can't really serve that function. But another development of the calculus of the pendulum actually gets it from the Para-digm Circle. And that's an example, I think, of using a very abstract representation like that of the calculus, but deriving it by means of visual images, which I think can be a really helpful transition. I guess I'm still kind of resisting the notion that I thought was implicit in your original question, that mathematics itself has a certain character or doesn't. It seems to me it's one of those things that we can use in many different ways. And Maxwell, for example, was somebody who used it in a way that I think was really visual, and that he did so deliberately, and that, you know, other of our authors really run away from the visual, perhaps feeling that anything that is visual by nature is imprecise. So I want to preserve a spectrum of approaches to that sort of question.
I guess what I'd like to say in conjunction with that is it seems to me that when we plot the motion of a pendulum, say on a graph, we do so using the sine wave, and that we're seeing the motion of a pendulum in a different way when we do that, but we're employing calculus or basic algebra to do that. So I guess what do you, there seems to me to be different ways to utilize math to be able to see the motion of the pendulum.
Oh, yeah. Yeah, I completely agree. By the way, I think a lot of people would say the sine curve has already become a form in itself that we can understand. I complained about the graph that gives us the sine curve because really all we are able to measure is a number of individual places at individual times. And then we have to fill in, you know, connect the dots. And that raises the question I think my friend Terry was raising earlier. You know, do we really have a way other than just a kind of approximation to fill in the blanks between those dots? And I felt the vision of the Para-digm Circle is the thing that enables us, well, maybe I should say, it's an alternative image, an image that doesn't seem to start with the discrete and then require us to imagine a continuity. It seems to me it starts with the whole and allows us to deduce the discrete. So that's one reason I like it.
Thank you so much for your talk. It was really beautiful. And
thank you. And thanks for your questions.
So we've got a couple of questions lined up here. Miss Michael, I'm going to unmute you. Are you there?
Hi. Thank you so much for the lecture, Mr. Fisher. It was really cool. I just had a comment of the alternate view of the calculus that I remember sitting in class and looking at the sine and the sine wave that we get from the Para-digm Circle and how the derivation of sine and cosine will just alternate essentially. And I find that particularly beautiful, the way that it shows that there is no constant.
Yes.
Other than the constant changing.
Yeah. And it's that fact that the differentiation of the sine gives the cosine, the differentiation of the cosine gives the sine. It's clear that it'll never come to an end.
Yeah.
And in a certain way, I think that's why, well, I guess I said this, why one way of trying to understand the pendulum motion is doomed to failure because it's an infinite task. Did you have more to add?
Oh no, I just wanted to share my view of the calculus.
Yeah.
And that, thank you.
My
Thank
pleasure.
you. Thank you, Ms. Michael. I think we will take a question, and again, we've got a few lined up here, but we'll take a question from Mr. Cordova.
Can you hear me?
Yes.
Okay. Mike, I mean, it's kind of tangential, but I'm kind of thinking of the nature of pendulum, and you kind of said this, so I'm just going to read the question I typed up, but you referred to the deeper, more essential root character and the nature of the pendulum. Maybe this could be said to be the nature of regularity. That is, does the pendulum itself serve solely as a tool for translating the regularity of the phenomena of motion? And thus, as we use calculus, or as we use the calculus to abstract values for these phenomena, are we just extrapolating the nature of our confused notions of motion and deriving a self-substantiated argument? And then I just had parenthetical comment, which as Mr. Stickney said, has a very Platonic nature to it.
Yeah, I'm glad. Let me go backwards because I meant to say something more about Mr. Stickney's remark about Galileo's Platonic character. I was long in seeing that, you know, when to the extent that Galileo was ever taught to ordinary science students, which was my education, he's usually taught as the one who's fighting against Aristotle. And the first thing I noticed when, you know, studying Galileo seriously, the way we do here, is Galileo gets a lot from Aristotle. And for me, the experience of seeing how much he draws on and respects Aristotle was so strong that it's kind of obscured the extent to which he also, you know, has a real affinity, I think, with Plato. So I was really glad that Mr. Stickney and now you have brought that up again. The other question you asked began with the speculation as to whether the really essential thing about the pendular motion is regularity.
Mm-hmm.
And I don't think so. I tried to give an alternative view at the opening of the talk because it seems to me there are a lot of regular things that don't draw us in quite the way that the pendulum does. And I felt that the kind of motion, you know, the back and forth motion of the pendulum has the ability to define a completed act that mere regular events may not always do. And then beyond that, it seemed to me if we try to look at pendular motion the way we look at, you know, simpler forms of motion, which might also be regular. You know, you've probably seen those toys that drop marbles one by one down a chute, and well, that's regular. As regularity of period, it's naturally accelerated motion. It doesn't seem to me that challenges our understanding the way the pendulum challenges us when we try to understand what are the intermediate positions. You know, beginning and end of the swing, that's no problem. Middle of the swing, it's kind of easy to understand. What about all those other phases of the swing? It's really tough. And yet they deserve to be understood too. So I guess I still would want to say the pendulum really stands by itself.
But I guess, and you kind of alluded to it, but even by its construction, I'm going to use the term self-substantiated, right? it's already completing its circuit and its regularity by construction.
Yeah.
And so I'm kind of looking at it as almost it's as a translation tool or a tool for translation, where and because we can't in a way, and I think other questioners were kind of alluding to it, but it's obscuring the phenomena it's measuring a little bit more, but by doing so, we're able to abstract like very specific values from its motion and from our observations of it. But it's not really telling us more about the nature of those phenomena or like velocity, acceleration, but it's telling us like the proportionality of their relationships. So it's in this like weird medium place or in between state.
Let me make sure I understand what you meant by it's obscuring the phenomena that we're looking for. Which phenomena do you think we are looking for?
I guess I'm thinking of I'm a junior as well, and also thank you. This was a very needed, I think, presentation. Not only beautifully done, but needed as well. But so I'm thinking of like the beginning of Galileo's two new sciences, and we're talking about time,
Oh,
distance,
okay.
and then speed or something like that, velocity, right?
No,
And those seem to be the crucial phenomena tied up in the motion of the pendulum and what it's measuring, and also in the calculus as well.
no, now I think I understand what you mean. I would put it this way, at least this is what I'm hearing from you. I'm a reader of Galileo. In fact, I'm one of his friends, and we're all there together. And to the extent that we are looking at motion in the way that they are looking at it, they make this wonderful, tremendous progress by discovering that we can find a constancy in what appeared to be inconstant. But then when we try to get to the pendulum, it doesn't work. And I would agree with you that the pendulum really obscures natural motion or natural acceleration. Mm-hmm. So yes, if that's what we're looking for, boy, I would sure never start with the pendulum. But it turns out that Galileo does give us some a way to begin, and the only mistake I think we would make is if we see Galileo as the end of the story. If we see him as the beginning of the story, then it seems to me we can go right from his proposition 6 to a different approach like that of the Para-digm Circle. And you probably remember that he's really interested in the circle, right? Mm-hmm. In other parts of the two new sciences.
Yeah. And I guess that is for me where his attachment to the Aristotelian and Platonic arguments lies, is that he's getting at this question of, I guess, nature. You said at a point like the unity of an infinite sequence. Mm-hmm. And so that in a way, moving from Galileo, we're being asked, and moving towards the calculus, we're being asked to redefine our concept of natural motion or naturally accelerated motion. And if that is truly natural, like one of my kind of ongoing questions with the lab this year is just where is nature and what is nature in the hierarchy of this argument of calculus?
Yeah, did anyone in your class or in any of the classes of the people who might be listening in, did the question ever come up what Galileo means by the nature in natural acceleration? Because it's not clear to me whether nature in that sense for him is part of a much larger thing called nature.
Yeah, it seems he's already pushing, there's already a push for an argument of nature as like this abstract, purely abstract mathematical concept or something like that.
I don't know. I would be hesitant to reduce Galileo to that point. Mm-hmm. It's what I feel is a tremendous tension between the phenomena that we all somehow recognize as by nature, and the ability of geometry in his hands to articulate that phenomena, that phenomenon. But I never get the feeling that he thinks one is to be reduced to the other.
Mm-hmm. And kind of, I guess, hence calculus can't, and that's your point, calculus can't give us every answer.
Well, I don't think calculus can do anything. We can do things
Okay.
with it. and I think, there have been thinkers who have done a wonderful job of expressing just, the most incredible variety of things in the language of calculus, from which we learn an enormous amount. But whether or not we would want to say they've reduced it to calculus, that is, that everything but what we are able to express in the language of calculus is merely ancillary. I guess I've never been willing to go that far in any area.
Thank you.
Thank you, Mr. Cordova. Thank you, Mr. Fisher. I'm going to take a question from Dana Densmore, and then Don Lemons has another question, has been waiting for a bit. Dana.
Hi, hi, Walter.
Hi.
That was great, Howard. Thank you so much for that. I want to go back to, well, the conversation on this is still going on, but I want to go back to the point where you were, I think it was answering Michaela's question, and you were addressing this idea that some people want to see it. They want something that can be seen. And other people are maybe suspicious of that and want to just stick to the mathematics, which is solid and dependable, perhaps. And what that made me think about is Newton, somebody, of course, who invented an analytic calculus, but chose for his Principia Mathematica not to use that, but to use he invented a whole geometric calculus in order to have something where you could see what was going on, where it wasn't just formulas. And of course, he didn't use the algebra either. Even that was something that could not be seen. And therefore what? You don't know what's going on. And so he has a slightly obscure thing in the preface about wanting to do it that way because we're looking at the work of the most perfect mechanic. And I think that has something to do with to be able to have this direct connection, direct sight of the work of divine being. So what do you think about that he made that choice?
Yeah, no, I think that's a wonderful example. And there too, I'm going to go back to my physics school days when Newton was presented as the one who left the ancient world behind, because behold, we have these formulas. And then, much later in life, learning that, well, Newton didn't have those formulas. Yeah. Newton had as you pointed out, a mathematical geometry or a geometrical mechanics. I like having examples of fundamental writers that live in what we've been taught to think of as two different worlds, because it's clear that for them, they aren't two different worlds. And I've almost learned to take it as a red flag whenever I feel a tension between two ways of representing a problem. It's a caution to resist thinking that, oh, well, one of them must be right and the other must be wrong, or one of them must be better than the other. It seems to me we should start questioning whether they really are different worlds, and whether they really do exclude one another, and whether in fact there isn't a more comprehensive way of embracing both. And I'm so glad you brought up Newton, because he's a wonderful example of that.
Thank you.
Thank you.
Thank you, Dana. Okay, Don, you've been waiting for a while. Do you still have your question? I know you wrote it, or you wrote a version of it. Are you there, Don?
Don, I can see your video, but I can't hear you.
Okay, how about
now? Now we see you. Now I hear you.
Okay, so my question has to do with the last part of your talk, in which you were talking about how Huygens, by exploiting the cycloid to make even larger pendulum swings isochronous with the smaller ones. And that seemed like a wonderful idea, but it didn't work out in practice. And your expression was that by attempting to make this perfect, he actually did the opposite. He made the design worse. And I'm wondering if that is, you see that other places in the history of science, maybe especially in the things that you study as undergraduates, or is it a general thing? I mean, I don't know. It's just an interesting idea. And I wonder if you could say more about it.
Yeah, I'm not sure I can come up with any examples from the history of science. But it seems to me that we tend to have a simplistic idea of the perfect. And because we're all familiar with the phrase, the perfect is the enemy of the good. That's not quite what's going on here, but the problem is that if we're living in the cave and we see a glimpse of the form or the sun, and we want to follow it, it's not completely clear how to follow it. And I guess I saw Huygens's attempt to manufacture a real cycloid, because the cycloid actually does have the property of isochrony, as a way of, I don't know, too literally trying to imitate the perfect. And I'm sure we can build a cycloidal pendulum that overcomes the problems of greater velocity. Like we could put it in a vacuum. We can build a cycloidal pendulum that has less friction on those ears. And by doing a whole lot of other things along with the cycloidal path, we might actually make a really, really good isochronous pendulum. But look at all the other problems that trying to resemble the Para-digm Circle in what seemed to be the most obvious way. Look at all the other problems that brought about. And I guess I wanted to contrast it with taking the simple pendulum, which once we really look at it, and I think the Galileo proposition 6 really shows us that, well, the simple pendulum really can't be isochronous, but
Yes.
it can approach isochrony. That's a different way. It's not as obvious because there's nothing in the Para-digm Circle that says that anything ought to depend on the size of the circle.
Yes.
So I guess, I hope I'm not just repeating what I said in the lecture, but I guess I do feel it's a general problem when we're trying to do the very best. It's not easy to know what the path to the very best looks like.
Yes. Yes. Yeah. Thank you.
Thank you.
I'm actually not sure if I lowered Dana's hand before or not. Dana, did you have another question, or is that from before?
That was from before. Thank you, Walter.
Okay, sorry about that. It might be that we don't have another question queued up, so we'll wait for a moment here and see. We do have one now. Mr. Bill Donahue has raised his hand, and we will allow him to talk. Hi, Bill. Are you there?
Well, I see a screen for Bill, but there's no microphone.
And Bill, I don't think you're muted, but we're going to mute you. I think you're getting feedback there. Are you there?
Yes.
You've got maybe 2 devices going on or something like that. We'll give you one more chance if there's something you can turn down. If not, maybe we'll ask you to write it. But I'm going to unmute you at our peril one more time.
Okay, let's try this. No, it's still not working.
Probably some pendular motion in there somewhere. Bill, I'm sorry. I'm going to go ahead and mute you because of the feedback. We have a question queued up, and maybe you can work on it and try to come back or write your question. So Carrie Stickney typed in a question. I wonder if Tocqueville's attempt to modify the path of young democracies by carefully distinguishing liberty from equality is an example of departing, quote unquote, more from the ideal in practice so as to avoid frictions in the practical world. Maybe this is getting more to your perfect being the enemy of the good, Mr. Fisher. I don't know if you're prepared to shift gears. I suspect you are.
Yes, in fact, I suspect that the best examples probably come from history and political science rather than from the history of science. Yeah, it's a wonderful example. Help me remember, did Tocqueville ever explicitly state that liberty and equality together would constitute the most perfect society, so that pursuing one in preference to the other, at least to some extent, would indeed for him represent an indirect path to the perfect.
I don't know if Mr. Stickney is available to either step in by writing or raising his hand. It looks like, so Carrie, you should be able to talk, I think now.
Yeah, can you?
Yeah,
Can you
yes.
hear me?
Yes.
Very good. Well, yeah, I think sometimes he is so suspicious of the abuse that growing equality of conditions seems to bring with it, but that he also sees the ways that it has been in the service of liberty, or has been an ally to liberty, and he sees that there's something, I think, simply true about the equality of conditions, so that it's as though in a perfect world there would be perfect equality of condition, which would not lead to the loss of initiative in the citizens, or a kind of almost certainly tyrannical centralization of power. So yeah, I think he does. He keeps, I mean, reading him is such an interesting exercise, because at various moments you think you understand what he means by each of those terms, liberty and equality, and he continues to modify them and show their interactions on one another. But it seems as if his warning about equality somehow taking over and effacing liberty somehow, that equality is the path of least resistance in a certain way, and liberty will die without continued effort. It will produce he's hoping it will produce various kinds of secondary structures, all of which may seem at various times to conflict with liberty, at least liberty understood in a certain way. So that, yeah, I think it's a wonderful thing to try to think about, and that he too is thinking, as he sometimes puts it, there's something in God's plan that is leading us to greater equality of condition, and it's our job not to let that go astray, or become its own worst instantiation.
Yeah, you know who else I'm thinking of is Hobbes, because there it seems to me the perfect is the ordered, and
Yeah.
Liberty turns out to be really incompatible unless it's highly restricted, but equality turns out to be right, perfectly compatible.
Yeah. With all that.
As long as there's one exception.
Yeah, that's right. That's right. No, that's an excellent kind of extreme case that illuminates the situation. Yeah. No, I thought right away that the good examples would probably to be found in political thinking and history.
Yeah.
And that it's very admirable when statesman-like behavior can strike a balance between things that works for the citizens and also comes closer to justice.
Now, I mean, an obvious problem, and Tocqueville talks about this. I don't remember that he talks about it very much in the sections we typically read, but this is my recollection. The problem for a responsible political leader is that it's much easier in a democratic society for people to understand a clear, direct path to the ideal. And it's very easy to get people, enthusiastic about that path. But if the actual path to ameliorating conditions is indirect, it can look like shilly-shallying, a lack of enthusiasm, and not very exciting. And it seems to me democracies face exactly that problem.
Yeah, I agree.
Okay, thank you, Carrie. I think we do have Bill Donahue may be coming through on a different line. Are you there?
Yes.
I am here.
Right.
Okay, I'm just taking over Dana's computer for a moment. And I don't really know what to do with, where to go with this idea, but the thing that is really for me, really characteristic of pendulum motion is that I'm still back in step one of the lecture. It's the same again, where and I'm thinking of the paradigm circle also, where you have the line that represents the change, that is the acceleration line, is exactly opposite the line of the motion. And it looks as though there's something about time going on here, where a later state, or an earlier, I don't know which way to put it, an earlier state is reaching forward through time and making something happen later on, or the thing that happens later on is somehow looping back around. You have, the tech people call it feedback, but it seems to me I've been reading a lot about entropy, and that goes in a completely different direction. That just kind of everything falls apart. This is something that seems to build on the past and try kind of to reinforce things. And I just wonder, I don't know where to take that at this point.
Well, it gives me an idea. Because my talk really dwelt almost exclusively on the geometrical aspects of the motion. But it seems to me what you're bringing up is the mechanical aspects. And any pendulum is going to have to combine something like mechanical inertia and something like elasticity. Now, the gravitational pendulum isn't exactly elasticity, but right, the suspension directs the force.
It follows the elastic principle.
Yeah, which is the proportionality of acceleration to distance. So if we think of an elastic material, I think that's the place where your question really becomes wonderfully interesting. Because I would put it this way, in the elastic material, is it the stretching that calls forth the force? Or is it the force that diminishes the stretching? And how can they possibly be simultaneous? Because that would imply that one doesn't exert a causal relation on the other. And if they don't exert a causal relation on the other, how on earth can they possibly be connected? And it seems to me, we read a little bit of Leibniz about elastic materials. We read, I forget who else. Gosh, I'm not sure we do read anybody else about elasticity, but it is the most mysterious thing. How can these two things be connected? They're both physical properties. They're both physical influences. How can they be connected other than causally? But if they're causally, how can one not be prior to the other? So I think it's a complete mystery. I don't know. Can you take us any further than that?
I fear that I can't. Not at this point.
Well, in moments of excessive enthusiasm, I think all tutors and former tutors instantly say, "Oh, that ought to be a part of the program." So, I'm envisioning a whole series of studies on elasticity, which I suspect will never happen, and probably for a good thing. But boy, it's an interesting topic.
Yes. Yes, indeed.
Thank you. I have a couple more written questions. Mr. Fisher, are you holding up?
Absolutely.
Okay. I'm going to take one that is directly, I think, commenting on that exchange. And this is from Don Lemons again. Comment: the physics term that possibly describes the reaching back in time that Mr. Donahue mentions is that the pendulum motion is deterministic. And that is indeed very different than the typical uses of entropy. I don't know if you can do anything with that, Mr. Fisher, or want to.
Well, Don is sure the one I want to hear more about from on entropy, but let me see if I understand that remark. If I guess I have to understand it as something like an appeal to a nature. If having built a device like a pendulum in a certain way and with certain materials, we say that it now has a nature in some restricted a way, all of its behavior is going to flow from that nature. And I guess we generally make an assumption that something that has a nature doesn't change its nature merely by displaying it. But I think from the point of view of a deterministic science, we would probably have to say that if there, to the extent that there's such a thing as entropy in the world, natures do change in the process of exhibiting their nature, because all activities have some effect. Well, almost all activities, all but the most perfect activities have some effect on the store of entropy in the universe. And therefore, the future will not be exactly like the past. So I hope that's somewhat connected with Don's thought.
Yeah, I think you re-expressed it in a very interesting way. I tend to think of these, physicists have models for different processes, and some of them are deterministic and some of them are not. And, when you start studying physics, I mean, the pendulum or the simple harmonic oscillator you mentioned is one of the very first deterministic systems you study. That doesn't, I tend to think of those as models, and that the actual fact of things is different. I mean, it's only approximated by our models.
Sure. Well, that's why the pendulum clock has to have a spring or a weight, right? Because the pendulum by itself will run down.
Yes.
I think this other comment we have in a way is maybe a variation on what you all are talking about. And this is Terry, and he writes, in the real world, we are faced with the reality of tolerances. We approach perfection by reducing tolerances, but only asymptotically. The process practically must stop with good enough. For example, once we have exceeded the diffraction limit, there is no point in perfecting the optical surface any further. Once the piston fits within the cylinder, there is no point in lapping them together further. We come to perfection, in quotes, only ideally, conceptually. The calculus is a way of helping conceptualize and to perhaps fix the bugs in our thinking, but the calculus is only a model of the reality.
Yeah, I think that's very well stated, Terry. Thank you. And one of the things I like about putting it that way is it reminds us that there isn't necessarily a single path of approach to the perfect. The way you put it as, minimizing or reducing tolerances, there are all sorts of variables whose tolerances we may reduce. And they aren't independent. I mean, you gave the example of it. There's no reason to reduce a tolerance of fitting once the thing fits. But I would also say that there's no point in trying to reduce the tolerance in one variable if we are still going to be limited by a second variable. So again, I think it takes judgment, and by a variety of paths, we may be able to approach the perfect. But I'm also trying to look from the standpoint of somebody who doesn't really know what those independent factors are. Maybe they haven't seen or haven't understood the analytical analysis of it. And so they don't see why we shouldn't keep trying to reduce this because they're not aware of the opposite factor. So that's maybe the engineering analog of the citizenry who doesn't see why we shouldn't keep trying to do better and better and better in one measure of social good through failure to realize that there's another big one waiting in the wings that we've got to address because it's more urgent.
Thank you. See, one more written question, and maybe this would be a fitting one to end with that we can see. So this is from Mr. Chapagain. I'm not a junior yet, but based on your lecture, I was fascinated by this idea of isochrony of descent along the chord and how that idea seems to be paradigmatic, as that idea eventually leads to our understanding that the pendulum doesn't show pendular motion, but simple harmonic motion. If you were asked to explain this concept to an 8-year-old, how would you do it?
Okay. I've got to divide your remark into two parts. First of all, just one clarification. To the best of my knowledge, nobody else in the world uses the phrase pendular motion. I just wanted a term that didn't already have a lot of technical associations the way simple harmonic motion does. So strictly speaking, I would have to say that the motion of an ordinary pendulum, which I'll call pendulum motion, is not simple harmonic motion. That simple harmonic motion is governed by the Para-digm Circle, or the principle of the acceleration being proportional, strictly proportional to the distance. And as I tried to show, and as I think the Galileo proposition shows, that is not strictly true for the simple pendulum. And when you say, if I were asked to explain this concept to an 8-year-old, I need a little more clarification from you on what this concept is. Do you mean, how would I explain the difference between simple harmonic motion and what the simple pendulum actually does? I'm going to assume that you mean that. And that means I would be trying to explain the difference between a concept of perfect motion and what the pendulum really is doing. Here's just, it's been a long time since I've been asked to say anything to an 8-year-old. Here's what I would come up with, just my first thought. I would take a simple pendulum and I would try to get a very long one, maybe, 8 or 10 feet, something like that. and get a stopwatch. And, you know, depending upon the 8-year-old's experience, we might want to do a few little exercises with the stopwatch just to make sure that the 8-year-old has a good sense of what the stopwatch is supposed to do. And then I would compare a lot of small deviations of this very long pendulum. So maybe oscillations having a 6-inch amplitude, and then having 1 or 2 foot amplitude. Okay, and my guess is, because I think I actually did this once, my guess is that the stopwatch would not be able to show any significant difference between those two. Then I would pull the pendulum way back to a 4 or 5 foot displacement and measure the swing time. And I bet we would find quite a big difference. Then I think the best I could say is, you know, we might have to talk a little bit about pendulum clocks, but I think I would say that, you know, if a pendulum clock is supposed to keep the same time no matter what, that would, we would want it to have the same time for large swings and small swings. And clearly our pendulum isn't really doing that. And then that would prompt the question, well, is there something that does do that? Oh, that's about the best I can come up with at the spur of the moment. Have you got any particular 8-year-old in mind? And would you like to try an experiment and see how well that works on your 8-year-old of choice? I'm sorry, I keep forgetting this was a chat. This wasn't a live talk.
I have 9 and 11-year-olds that we could recruit, but maybe we'll do it on another occasion.
Okay.
Mr. Fisher, I think this might be a fitting time to conclude. We don't have other questions queued up. It's been a wonderful lecture and question period. Would you like to offer any closing thought before we say adieu?
Well, just that I've enjoyed this so very much, and thank you to everyone who was tuned in, and whether you asked a question or not, it was really nice to see your presence. So thank you again. And I gather the question period, as well as the lecture itself, will be available at some time for future viewing.
They will. For folks who haven't checked, if you go to our YouTube page, we're steadily getting these edited and uploaded, and so there's a little bit of a lag, but this will be up there, as will Mr. Fisher's lecture from the spring, hopefully in the next several weeks. So thank you all for attending. Stay tuned for coming events, and thank you again, Howard, so much for a lovely occasion.
My pleasure. Thank you.